If you want to understand circular motion, I think one of the first things you have to think about is if you have an object that you want to keep traveling in a circle. So say that white line denotes the path of that box there. If I want that box to continue traveling in that circle at a constant speed, which way should I pull it? And we'll try drawing some arrows on this box just quickly. This isn't a theory lesson, but I like this exercise. If we pulled the box this way, and it had starting velocity that way there, the path it would take would be something like that. The path would be yanked in that direction there. If it had that same starting velocity, so that yellow arrow to the left, and we pulled it in that direction there, and that's the answer that a lot of people who don't do physics give. Yeah, they say pull it along the path there. We expect the path of that box to be something like that. Or if we keep adjusting that red arrow to follow the line of that white path, we sort of end up with something like that. But if we try to pull the box towards the center of the circle, like so, the path of that blue box will follow the white circle exactly. And here's where it finally made sense for me. We talk about that box moving around that circle at a constant speed. A constant speed means a constant kinetic energy. And a constant kinetic energy means there's no work being done on that object there. If there really is no work being done on it, there's no force in the direction of motion, so forces can't be like that, forces can't be like that. And if we can't have a force in the direction of motion, the force is either going to be perpendicular to the direction of motion like that, or straight down. And of course it's straight down because the other force leads it in a circle in that direction there. That's quite interesting. If that didn't make sense to you, let's just move on to the formulae. And if you master the concepts of work or energy, maybe that explanation will help you out a little bit. So first of all, if the object moving in a circle really does need to be pulled in that direction there, that is the direction of the acceleration, and it's also the direction of the centripetal force. And that's the force that keeps the object moving in a circle at a constant speed. If we make that object move more quickly, so if we increase the speed, the acceleration also increases. It has to be pulled at a higher rate towards the center of the circle. Of course, it never actually moves towards the center of the circle, just around in that circle, in that circular path there. If we also make this white path smaller, then we have to pull harder. And this is something that people intuitively grasp when they go to a children's playground and stand on one of those, I don't know what you call them, they're circular rotating platforms. The closer you move to the center, no, that's not quite true. The closer you move to the center, the velocity goes down. No, that's not right. Well, basically, the smaller one of these is, if you are moving at the same speed in a smaller circle, so we can't actually model it here, it'll take a lot more force to keep you moving in that circle. I'm thinking of this other invention I've seen at science museums. I don't know how common it is. Sometimes you see them in children's playgrounds. They're basically stands like this with handles here and a pivot down the bottom, and you stand on them like this, and you get someone to push you around like that, and when you pull yourself further in, you're reducing the circle that you're moving in, and it actually becomes a lot harder to hold yourself up, so the acceleration is increasing. Let's skip over this theory for a second because I'm wasting time. This is supposed to be a practice question lesson. Let's set up a practice question. A skateboarder and skateboard of combined mass 82 kilograms is moving in a circle of diameter, there we go, diameter 18 meters. Question 1 will be to figure out the velocity. Oh no, we'll say actually question 1 will give the velocity as 8 meters per second. And our goal will be to figure out the period, the time it takes them to move around one full circle, the centripetal acceleration, and then the net force on the skateboarder and the boy. So, he's moving at 8 meters per second. We know the velocity, we can figure out the radius of the circle, and we can therefore figure out the period because there's only 3 unknowns in here. We know what 2 is and we know what pi is. The radius of the circle he's moving in is not 18, 18 is the diameter. The radius is 9 meters. So, let's figure out the circumference of this circle. Circumference is equal to 2 pi r, that's 2 pi times 9, and that's around about equal to 18 times pi, 56.55 meters. This is also the distance he travels when he goes around the circle once. We know the other formula, distance equals velocity times time. So distance over velocity equals time. The time it takes to complete one full circle is equal to 56.55 over 8, which comes to 7.07 seconds. So the period is equal to 7.07 seconds. You might get a slightly different answer because we're approximating pi. Now the centripetal acceleration. We'll find it in 2 ways. First of all, we'll use the formula AC equals v squared on r. So the centripetal acceleration is equal to v squared, that's 8 squared, divided by 9. That's 64 divided by 9, or 7.11 meters per second squared, since it's acceleration. But I've also got this other formula up here. The difference between this formula, which gives centripetal acceleration, and this formula is that the first one requires that you know the speed and the radius of the circle. The second one only requires that you know the radius and the period. So you always need to know the radius, but depending on whether you know the speed or the period, you're going to have to choose which of those formulae you use. So let's use the other one. AC is equal to 4 pi squared r on t squared. That comes to 4 times pi squared times 9 on, what was t, 7.07 squared. I'll try that. 4 times pi squared times 9 divided by 7.07 squared. I have 7.108, which is very close to 7.11. Can you think of any reason why it's better in this case to use this formula than this formula? The answer is that we started off the question being given the velocity, and then we worked out the period. What if that answer was wrong? Then that would affect the next answer in our question. So it's better to use what we have. Furthermore, to find the period, we approximated pi. That's why the answer I got on my calculator for this sum was not exactly the same as the answer for this sum. Wherever possible, use the numbers you're given and avoid using your approximations. Finally, the net force. We know Newton's law, F is equal to ma. Therefore, Fc, the centripetal acceleration, is equal to the mass times, Fc, the centripetal force, is equal to the mass times the centripetal acceleration. That's why this formula here and this formula here are the same, except the second one is multiplied by m. And the same goes there. The second one is multiplied by m. So finding the net force now, that's equal to, I can either just say mass times AC there, which is equal to 82 times 7.11, 583. Or just as an exercise, we can go and use one of these formulas here. What should I say, formulae? mv squared on r is equal to 82 times v was 8 squared divided by 9. 82 times 8 squared divided by 9 should be, yep, 583.1. Why then, which should I use? I'm actually going to use my second answer, 583.1, because these figures here are not approximations, whereas that figure there is an approximation to 2 decimal places. Let's solve this question now, assuming we weren't given the velocity and we were just given the period. The period is equal to 12 seconds. And again, we'll say, what is centripetal acceleration? What is the net force? And what is the velocity? Going from period to velocity, we can't really use that formula as it is. We're going to have to rearrange it. Multiply both sides by t, so we get t times v equals 2 pi r. Divide both sides by v, that v cancels out, we get v there. So the period is equal to 2 pi r on v. So v is equal to, oh sorry, what have I done wrong there? No, sorry, that was what we should be doing before. For this question, we can just leave it as it is because we're trying to get v by itself. So velocity is equal to 2 pi 9 on 12. 4.71. meters per second. So in the first question we answered, we had the speed was 8 meters a second, and the period was 7.07 seconds. In this case, we have a longer period, so it's taking him longer to make that trip around the circle, and therefore he's moving at a slower speed. 4.71 is less than 8. Let's find the acceleration. We won't use the formula with v in it because we've worked out v ourselves. Let's use the formula with t in it. So centripetal acceleration is equal to 4 pi squared times r, which is 9, on t squared, that's 12. So 4 pi squared times 9 divided by 12 squared. Never forget this squared down here. So a lot of people make that mistake in VCE. I have a centripetal acceleration of 2.47 meters per second squared. So 2.47 meters per second squared. Stop and notice something for a second. The centripetal acceleration we found before was 7.11. And that was when he was traveling around this same circle at 8 meters per second. We've almost halved the speed he's traveling at. But 2.47 is only 30% of the previous centripetal acceleration. And that shows that if you slow down just a little bit, going around in a circle, you can very quickly reduce the centripetal acceleration and therefore the centripetal force. So we'll find the force now. Net force, we'll use this formula here. 4 pi squared times 9 times 82 divided by 12 squared. That is 202.3 newtons. So the force has also gone down quite a bit. So if you slow down, you can significantly reduce the force. Circular motion questions get more difficult when we start to incorporate gravity, because then you force is either acting in the same direction, so gravity could be contributing to that centripetal force, or even at right angles, which we'll look at in the next lesson.